Hello, and thank you for joining us today. I'm Jennifer Simpson, Executive Director of the International Titanium Association. Welcome to the Fundamentals of Titanium. The International Titanium Association, also referred to as the ITA, is a not-for-profit networking trade association serving the titanium community worldwide. Established in 1984, the association's main mission is to connect the public interested in using titanium with specialists from across the globe who may offer sales and technical assistance. ITA also sponsors educational workshops, manages a variety of technical and marketing committees, and hosts the only annual conference and exhibition dedicated exclusively to the titanium metal industry. The association benefits from having a wide variety of membership organizations consisting of producers, fabricators, suppliers, end users, consumers, and academia from over 20 countries worldwide. The Fundamentals of Titanium course has been given extensively throughout the world and will be translated in over 6 different languages. Upon your completion of the Fundamentals of Titanium, you will receive a certificate for 8 hours of continuing education certified by the International Titanium Association. So sit back, enjoy the presentation, and the dynamic information presented by Stanley Siegel, who is one of the leading experts in the titanium industry and whom we have been so fortunate to have as our fundamentals instructor for the past 10 years.
There are 3 main characteristics that define titanium's usefulness. The first one is strength to weight ratio. Titanium is very strong and it's lightweight. It is 60% the density of steel and has the same strength. This results in a very efficient material. Second, it is very good at high temperatures. If Icarus of Greek mythology had titanium wings rather than wax, he might have survived. The very high strength at elevated temperature results in the interest of titanium for jet engine applications. Titanium is very good at up to about 1100 Fahrenheit or 600 centigrade. It also has the best strength to density ratio of all metals up to that temperature. The third and very important property, particularly nowadays as we move into new markets, is titanium's outstanding corrosion resistance. We will review this in detail in session 8. Titanium is immune to essentially all seawater and all natural salts. The VAR process is depicted here. The primary melt is made from compacted briquettes. The primary melt becomes the electrode for the second melt or final ingot. This depicts the details of the actual melting furnace. The metal is melted by a DC electric arc maintained between the electrode and the crucible. The electrode is gradually consumed and an ingot is formed in the bottom of the crucible. Note the crucible is copper. Recall carbon and oxide crucibles were initially tried, but they reacted with the titanium. This is called a cold mold process. Copper, as we all know, is an excellent conductor of heat. On the outside of the copper crucible is water, which cools the copper. So the titanium is melted in a water-cooled copper crucible. This is an inherently dangerous process. If the electric arc would wander or move to the copper, water would enter the furnace, causing an explosion. Safety in melting will be discussed in session 13. This video shows an ingot being forged at TIMET. Here we see a manipulator pulling an ingot out of the furnace. Temperature here probably is above 2000 Fahrenheit. This manipulator will take it over to the forge press, and it's what we call upsetting the ingot. And you can see the titanium oxide coming off the ingot as it was upset. Now we see it further in the process where it's actually being forged to basically a round or an octagon shape. The ends show some cracks, but that will be cut off eventually. Now we have an interesting operation where they're cutting this billet hot. So now we have 2 billets instead of 1. Titanium is an allotropic element, which means it can exist in more than one form. These forms again are alpha, which is hexagonal close-packed structure, and beta, which is body-centered cubic. Metals that have a cubic structure are generally very ductile. The temperature at which these phases can exist is dependent on alloy composition. The lowest temperature at which we have 100% beta is called the beta transition. The first one is superplastic forming, commonly called SPF. We discovered that several titanium alloys are unique in their ability to very uniformly deform at temperatures around 1550 Fahrenheit. We can form very complex shapes utilizing this technology. However, the temperature and rate of deformation must be closely controlled. This graph illustrates the process for producing the complex hat shape shown on the bottom. A titanium sheet is placed on top of the die, and then the assembly is clamped together and placed in a furnace at typically about 1550 Fahrenheit. Once in the furnace, argon gas is bled at the controlled rate behind the sheet and blows the sheet over the die very slowly. As it deforms, the sheet fills the whole die, and this part will assume the desired shape. Again, this process is called superplastic forming. Offshore energy extraction applications is an area of increasing interest for titanium. A few of the characteristics important in this area are strength, corrosion resistance in seawater, low modulus or flexibility, low density or lightweight, and good fatigue strength in seawater.
Mr. Siegel has been involved in the titanium industry since the industrialization of the metal in the early 1950s. He spent the early portion of his career developing titanium alloys in the research department of what is now RTI International Metals. Several of the alloys he developed are being used in both aerospace and commercial applications. After about 15 years in the lab, he moved from research to marketing, where his efforts were developing non-aerospace applications. Stan was very much involved in introducing titanium to the pulp and paper industry. He also promoted titanium for use in the oil and gas industry and dabbled a little bit in automotive. After his tenure in marketing, Stan was promoted to Vice President of Technology at RTI, which included responsibilities for the production area as well as marketing, research, and development. After 38 years, he retired from RTI and has pursued consulting work, which includes presenting this course on behalf of the association. No matter if you are new to the titanium industry or simply continuing your education, and regardless if you are a metallurgist, engineer, or a sales representative, you will benefit greatly from this information and from the convenience and ease of use this web-based course offers. And remember, should you need technical support or require any assistance while taking this course, just call, click, or visit the ITA. Staff members are always standing by. I'm Jennifer Simpson, Executive Director of the International Titanium Association. Good luck.